December 19, 1944, Ardennes Forest, Belgium. Major Heinrich Vogel of the 3rd Panzergrenadier Division crouched in a snow-filled crater, watching American artillery shells explode with impossible precision overhead. They are detonating without hitting anything, not the trees, not the ground, just exploding in mid-air at exactly the right height to maximize shrapnel spread. How are they calculating this? The pattern repeated with mechanical consistency. Shell after shell burst at precisely 20 to 30 meters altitude, creating overlapping clouds of fragmentation that turned the forest into a killing field. Vogel had commanded infantry through 3 years of Eastern Front combat. He understood artillery. Time-fused shells required gunners to calculate exact detonation timing based on target distance, shell trajectory, and time of flight, a complex calculation that varied with every shot. Even experienced crews achieved maybe one perfect airburst in 10 attempts. These Americans were achieving perfect airbursts with every single shell. Vogel pulled a battered notebook from his coat and sketched what he observed. Shell trajectory, detonation point, no visible impact. No premature explosions, no duds hitting the ground. Just consistent, devastating airbursts that caught his men in the open regardless of cover. He wrote a single word in the margin: unmöglich. This impossibility was slaughtering his regiment. 3 days into the Ardennes offensive, Germany's last desperate gamble to split Allied forces, American artillery had transformed from manageable harassment into an impassable barrier. Vogel's battalion had advanced 12 kilometers on December 16th. Today, they had advanced 200 meters and lost 40 men doing it. The phenomenon wasn't isolated to his sector. Radio reports from neighboring units described identical experiences. Perfect airbursts, impossible accuracy, mathematical precision that defied explanation. German officers were submitting after-action reports claiming American artillery had achieved supernatural fire control. What Major Vogel could not know, what no German or Japanese officer would discover until after the war, was that each shell calculated its own detonation point automatically using a miniature radar transmitter and receiver small enough to fit in the nose of an artillery projectile. The technology that was systematically destroying his offensive had been operational in the Pacific Theater for nearly 2 years, and the Allied forces had protected its secrecy so zealously that they had refused to use it over land until the desperate circumstances of the Battle of the Bulge made the risk acceptable. The revolution in warfare that Vogel witnessed wasn't superior gunnery. It was the VT proximity fuse, the secret weapon that would help save the American forces in Belgium and devastate Japanese kamikaze attacks across the Pacific. And its story began 4 years earlier in a research laboratory in Washington, D.C. The journey to this revolution had begun in September 1940, when the National Defense Research Committee, established just 3 months earlier, identified anti-aircraft fire as the most critical technical problem facing American defense. The mathematics were grimly simple. Conventional anti-aircraft shells required direct hits on moving targets, traveling at 300 to 400 kilometers per hour at altitudes up to 10,000 meters. Hit probability against maneuvering aircraft was approximately 2,500 rounds per kill. The solution required either impossibly accurate aiming or shells that didn't need direct hits. Time-fused shells could detonate near targets, spraying fragments across a wider area, but required gunners to calculate precise detonation timing for each shot. Against aircraft changing altitude and speed constantly, time fuses achieved perhaps 1,500 rounds per kill. Better than direct fire, still catastrophically inefficient. Dr. Merle Tuve, director of the Department of Terrestrial Magnetism at the Carnegie Institution, proposed what seemed impossible: a radio frequency proximity detector small enough to fit inside a 5-inch shell, rugged enough to survive firing acceleration of 20,000 times gravity, and reliable enough to function without premature detonation. The device would continuously broadcast radio waves and measure reflected signals. When reflection intensity signaled a target within approximately 70 feet, well within lethal fragmentation radius, the shell would detonate automatically. The engineering challenges appeared insurmountable. Radio tubes of 1940 were fragile glass envelopes requiring careful handling. Firing a 5-inch naval gun subjected projectiles to acceleration forces that would instantly shatter conventional electronics. The transmitter and receiver had to operate on battery power in a package weighing less than 1 kilogram, function reliably after months in storage, activate automatically after firing, and never detonate prematurely aboard ship or in the gun barrel. Development teams at the Johns Hopkins Applied Physics Laboratory, led by Tuve, Lawrence Hafstad, and physicist William Shockley, who would later receive the Nobel Prize for inventing the transistor, worked with unprecedented urgency. By December 1941, they had created prototype tubes capable of surviving gun-firing shock. By April 1942, complete fuse assemblies were passing laboratory tests. By August 1942, the first production models, designated Mark 32, were ready for operational testing. The first combat deployment occurred on January 5, 1943. The USS Helena, a St. Louis-class light cruiser operating near Guadalcanal, engaged Japanese aircraft using 5-inch shells equipped with VT fuses. Gunners had received minimal briefing. The shells were special ammunition requiring strict operational security. They were instructed to maintain radio silence about results and recover any duds without examination. At approximately 17:15 hours, radar detected incoming aircraft at 12,000 yards. Helena's 5-inch batteries opened fire at 17:18 hours. Japanese aircraft began exploding in mid-air without visible direct hits. Gunners watched targets disintegrate 200 to 300 feet from shell trajectories, far beyond what direct hits could explain. Within 7 minutes, all approaching aircraft were destroyed. Not a single bomb struck Helena or nearby vessels. Ammunition expenditure, 144 5-inch shells. Aircraft destroyed, 4 confirmed. Rounds per kill, 36. Against conventional anti-aircraft ammunition, requiring 1,500 to 2,500 rounds per kill, the VT fuse had increased effectiveness by a factor of 40 to 70. But the most significant result wasn't the numbers. It was that Japanese aircrew never understood why their evasive maneuvers failed. Pilots reported shells that followed aircraft and exploded by magic. Intelligence analysis of intercepted communications showed complete confusion about American anti-aircraft capabilities. The Japanese attributed improved effectiveness to better fire control systems, superior training, or classified aiming technology. None suspected the shells themselves were intelligent. This confusion was precisely what American planners intended. The VT fuse represented such a revolutionary advantage that its existence became one of the war's most closely guarded secrets, classified above the Manhattan Project in some assessments. Operational protocols prohibited use over land where enemy forces might recover unexploded rounds. Ships were forbidden from firing VT-fused ammunition within artillery range of enemy-held territory. Duds had to be recovered and destroyed rather than abandoned. For 18 months, the proximity fuse remained exclusively a naval weapon, deployed solely against aircraft over water where failed rounds would sink beyond recovery. The pattern that began at Guadalcanal repeated across the Pacific with mechanical consistency. Japanese aircraft attempting to attack American naval forces encountered an invisible barrier approximately 10,000 yards from their targets, the effective range of 5-inch naval guns firing VT-fused ammunition. They attacked the carrier task force off the Gilbert Islands on November 12, 1943. 27 aircraft approached. VT-fused anti-aircraft fire destroyed 19 before they reached bombing range. Rounds expended approximately 1,100. Average rounds per kill, 58. Against conventional anti-aircraft ammunition requiring 1,500 to 2,500 rounds per kill, the VT fuse had increased effectiveness by a factor of 40 to 70. But the most significant result wasn't the numbers. It was the Japanese aircrew never understood why their evasive maneuvers failed. Pilots reported shells that followed aircraft and exploded by magic. Intelligence analysis of intercepted communications showed complete confusion about American anti-aircraft capabilities. The Japanese attributed improved effectiveness to better fire control systems, superior training, or classified aiming technology. None suspected the shells themselves were intelligent. This confusion was precisely what American planners intended. The VT fuse represented such a revolutionary advantage that its existence became one of the war's most closely guarded secrets, classified above the Manhattan Project in some assessments. Operational protocols prohibited use over land where enemy forces might recover unexploded rounds. Ships were forbidden from firing VT-fused ammunition within artillery range of enemy-held territory. Duds had to be recovered and destroyed rather than abandoned. For 18 months, the proximity fuse remained exclusively a naval weapon, deployed solely against aircraft over water where failed rounds would sink beyond recovery. The pattern that began at Guadalcanal repeated across the Pacific with mechanical consistency. Japanese aircraft attempting to attack American naval forces encountered an invisible barrier approximately 10,000 yards from their targets, the effective range of 5-inch naval guns firing VT-fused ammunition. They attacked the carrier task force off the Gilbert Islands on November 12, 1943. 27 aircraft approached. VT-fused anti-aircraft fire destroyed 19 before they reached bombing range. Rounds expended approximately 1,100. Average rounds per kill, 58. They struck at the Marianas invasion fleet on June 15, 1944. 43 aircraft engaged American vessels. 31 were destroyed by VT fire. Rounds expended approximately 2,200. Average rounds per kill, 71. They attempted massive coordinated attacks during the Battle of the Philippine Sea on June 19–20, 1944. Intelligence sources indicate approximately 450 Japanese aircraft participated in what American pilots called the Great Marianas Turkey Shoot. VT-fused anti-aircraft fire from defending carriers and escorts contributed to the destruction of approximately 350 aircraft over 2 days. Combined with air-to-air combat, Japanese naval aviation lost 3/4 of its operational strength. The advantage extended beyond pure effectiveness ratios. VT fuses transformed the psychological calculus of air attack. Conventional anti-aircraft fire created dangerous but penetrable defenses. Skilled pilots executing proper evasive maneuvers could reasonably expect to survive long enough to deliver ordnance. VT-fused fire eliminated that calculation. Aircraft exploded regardless of evasive action. There was no skill-based counter, no tactical adaptation, no training that improved survival probability. Japanese pilots began reporting that American anti-aircraft fire was impossible to evade and more accurate than air-to-air combat. Some units documented anti-aircraft losses exceeding combat losses to American fighters, a complete reversal of earlier patterns where fighters caused 70 to 80% of aircraft casualties, while anti-aircraft fire accounted for 20 to 30%. American naval commanders monitoring classified effectiveness reports recognized they possessed a decisive technological advantage. Vice Admiral Mark Mitcher, commanding Task Force 58, noted in a classified assessment dated July 1944 that VT-fused ammunition had fundamentally altered the tactical picture, and that Japanese air attacks had become operationally unviable against properly defended task forces. The advantage depended entirely on maintaining secrecy. If Japanese forces recovered intact fuses and understood the mechanism, they could develop countermeasures, radio jamming, frequency modulation, different attack profiles. Worse, they might develop their own proximity fuses, eliminating American advantage entirely. But the advantage couldn't remain purely naval forever. The desperate circumstances at the Battle of the Bulge would force a choice between maintaining secrecy and preventing battlefield catastrophe. December 16, 1944, 0530 hours. The Ardennes forest erupted with the largest German artillery barrage on the Western Front since 1940. Over 1,900 guns fired for 90 minutes, targeting American positions along an 80-kilometer front. 3 German armies, 250,000 troops, 1,400 tanks attacked through snow and fog, exploiting weather conditions that grounded Allied air superiority. The offensive achieved complete tactical surprise. American forces, primarily inexperienced divisions refitting after heavy combat or green units in quiet sectors, faced annihilation. First Army Commander Lieutenant General Courtney Hodges reported defensive lines collapsing and unit cohesion disintegrating under overwhelming German pressure. By December 18th, German forces had penetrated 20 to 30 kilometers, encircled the critical road junction at Bastogne, and threatened the Meuse River crossings that would split British and American armies. The weather remained overcast, grounding aircraft. American forces lacked the reserves to contain the penetration. The offensive appeared on the verge of achieving its strategic objectives. Into this crisis, American commanders deployed the weapon they had protected for 2 years. On December 19th, artillery units received special ammunition shipments marked with red bands and classified handling instructions. Gunners were briefed that the shells contained secret fuses and must fire them exclusively over German-held territory to prevent recovery of duds. Battalion commanders received orders to employ the ammunition with maximum effect. Secrecy was now secondary to stopping the German advance. The effect was immediate and devastating. German infantry, accustomed to artillery shells that exploded on ground impact or occasionally achieved time-fused airbursts, suddenly faced something incomprehensible. Every American shell was detonating at optimal height to maximize fragmentation spread. Not 10% achieving perfect airbursts, not 50, every single shell. Captain Rudolf von Gersdorf, operations officer for the 7th Army, described the experience in a post-war interrogation. American artillery fire became impossibly accurate. Shells detonated at precise altitude above our advancing formations. We assumed they had deployed some new fire control system using aircraft spotters or radar ranging, but the weather made both impossible. Our casualty rates from artillery increased by a factor we estimated at 5 to 6 times normal. Advancing through American artillery fire became operationally impossible. The mathematics of the VT fuse transformed defensive artillery.
A conventional high-explosive shell detonating on ground impact created a fragmentation pattern approximately 30 meters in diameter. Fragments traveled in mostly horizontal or upward trajectories from the impact point. A VT-fused airburst detonating at 20 to 30 meters altitude created a fragmentation cone covering approximately 140 meters in diameter. Fragments traveled downward and outward in an umbrella pattern that was impossible to avoid by dropping prone. This meant each VT-fused shell had approximately 20 times the effective casualty radius of a ground-burst shell. Artillery batteries achieving the same effectiveness as before now fired 1/20th the ammunition.
Or more accurately, they achieved 20 times the effectiveness with the same ammunition expenditure. German forces encountered this transformation across the entire Bulge perimeter. At Elsenborn Ridge, the 2nd and 99th Infantry Divisions held against repeated attacks by the 6th Panzer Army. Artillery firing VT-fused shells turned every German advance into a slaughter. After-action reports documented German units suffering 40–60% casualties attempting to cross kill zones that were 500 meters deep. At Bastogne, surrounded 101st Airborne Forces received airdrops of VT-fused ammunition on December 23rd. Artillery supporting the garrison used the special shells to break up German infantry assaults that conventional ammunition had barely slowed. When the 4th Armored Division broke through to relieve Bastogne on December 26th, they found defensive artillery positions surrounded by German casualties in patterns that defied normal tactical explanations. Concentric rings of dead infantry 100 to 200 meters from American lines, all killed by airburst fragmentation. Lieutenant Colonel Harold Cohen, commanding the 463rd Parachute Field Artillery Battalion at Bastogne, reported, "The first fire mission with the new fuses took place on December 23rd at 14:45 hours. Target was German infantry in column formation approximately 1,200 meters from our position. We fired 12 rounds. Airburst detonations observed on all 12 rounds. Forward observer reported enemy column destroyed with estimated 80–100 casualties. Follow-up attacks against that sector ceased. We expended 237 special fuse rounds over the next 3 days. Every mission achieved airbursts. Every mission was effective beyond anything I had observed in 18 months of combat operations." Captured German officers interrogated in January 1945 revealed complete bewilderment. None had suspected proximity fuses. Most attributed the improved effectiveness to superior American fire control computers, better trained forward observers, or new artillery pieces with superior accuracy. When interrogators explained the actual mechanism, each shell contained a miniature radar. Reactions ranged from disbelief to stunned recognition. One Wehrmacht colonel remarked, "You put a radar in every shell? We were calculating firing tables for better time fuse settings. You made the calculations unnecessary. No wonder we couldn't adapt." The VT fuse hadn't just improved American artillery. It had rendered German tactical doctrine obsolete. Infantry tactics developed over 4 years of Eastern Front combat. Advance by rushes, use available cover, accept casualties crossing kill zones, worked against artillery that achieved 10% perfect airbursts. Those same tactics collapsed against artillery that achieved 100% perfect airbursts, covering 5 times the area. By early January 1945, the German offensive had stalled. Multiple factors contributed: improving weather allowing air support, arrival of reinforcements, German fuel shortages. But American commanders privately acknowledged that VT-fused artillery had been decisive in preventing breakthrough. The weapon they had protected for 2 years had justified its secrecy by helping save American forces from potential catastrophe. But while Germany was discovering the proximity fuse's existence in Belgium, Japanese forces in the Pacific were about to encounter it in an even more devastating application: defense against kamikaze attacks. The revolutionary technology that was devastating German infantry and destroying Japanese aircraft began with a brutally simple problem: how to fit a functioning radar system into a package 127 millimeters in diameter, 241 millimeters long, weighing less than 1.5 kilograms, capable of surviving firing acceleration of 20,000 times gravity, and costing less than $20 to manufacture in quantities of millions. The requirements originated in September 1940, when National Defense Research Committee Section T, responsible for proximity fuses, defined performance specifications. The device must fit standard 5-inch naval gun shells without requiring weapon modifications. It must activate automatically after firing and arm only after the shell traveled 400 to 600 meters from the gun, preventing detonation aboard ship or in the barrel. It must broadcast radio waves continuously, measure reflected signal strength, and trigger detonation when reflection intensity indicated a target within 70 feet. It must function reliably in temperatures from -40 to +70 degrees Celsius, withstand high G maneuvers from the shell's spin and trajectory, operate on battery power for up to 40 seconds flight time, and never detonate prematurely due to electronic malfunction. These requirements existed in direct opposition to 1940s radio technology.
Commercial radio tubes were fragile glass envelopes 5–10 centimeters tall, requiring careful handling. The smallest military radio sets, backpack models, weighed 15 kilograms and used 10 to 15 tubes. Radar systems, still classified technology in 1940, filled entire rooms with equipment weighing thousands of kilograms. Dr. Merle Tuve and his team at Johns Hopkins Applied Physics Laboratory approached the problem with radical solutions. They developed miniature tubes, designated T3 and later improved T8 models, only 25 millimeters tall and 10 millimeters in diameter. The tube envelopes used thicker glass and internal support structures specifically designed to survive shock. The filaments used tungsten wire in shortened lengths with reinforced mounting. The impossible mathematics appeared immediately. A functioning radar transmitter-receiver required 5 tubes minimum: oscillator, modulator, receiver amplifier, detector, and thyratron for firing circuit. Each tube required 1.3 volts filament power and 90 volts plate voltage. The battery pack needed to deliver this power for 40 seconds while occupying less than 1/3 of the available fuse volume. The transmitter antenna needed to radiate efficiently at approximately 200 MHz while fitting in the fuse nose. The entire assembly needed to withstand 20,000 G-forces during firing, equivalent to dropping a 2-kilogram weight from a height that would produce terminal velocity impact forces. The solutions required compromising traditional reliability standards. Commercial radio tubes operated at 2,000-hour lifespans. VT fuse tubes needed only 40-second lifespans. This allowed thinner construction and less robust designs that would fail after 1 minute but survived the critical 40-second flight time. Commercial circuits used conservative safety margins. VT fuse circuits operated at marginal voltages, 90 volts plate supply instead of the 120 to 180 volts typical of stable operation. This reduced battery size and weight but increased sensitivity to component variations. The safety mechanism was brilliantly simple. The fuse used a clockwork mechanical timer that armed the firing circuit only after 4 to 5 seconds, time for the shell to travel 600 to 800 meters from the gun. Before arming, the thyratron firing tube couldn't trigger regardless of received signals. This prevented premature detonation aboard ship from stray reflections off metal structures or during barrel transit from reflections off the rifling. It also provided safety against malfunction. If electronics failed before arming, the shell simply became a dud rather than a premature detonation. Development teams tested prototypes by firing them from naval guns at the Dahlgren Proving Ground in Virginia. Initial attempts in early 1941 achieved 40% survival rates. 60% of fuses shattered during firing. By August 1941, redesigned tubes achieved 75% survival rates. By December 1941, production standard T8 tubes achieved 90% survival rates. The final Mark 32 fuse design demonstrated 95% reliability. 5% of fuses failed to function, but only 0.1% detonated prematurely. William Shockley, who led theoretical analysis of detection patterns, calculated optimal detonation range. A 5-inch high-explosive shell produced lethal fragmentation within approximately 70 feet radius. Beyond 70 feet, fragment density decreased rapidly. At 100 feet, kill probability dropped below 50%. Closer than 50 feet, the shell might pass the target before detonating. The ideal detonation range was therefore 60 to 70 feet from the target. The radio frequency, approximately 200 MHz, was chosen specifically for this range. Lower frequencies would trigger at longer ranges, reducing effectiveness. Higher frequencies would trigger at shorter ranges, possibly missing fast targets. The 200 MHz frequency, combined with transmitted power levels of approximately 50 watts, produced a detection envelope that reliably triggered at 60 to 80 feet from aircraft-sized targets. The economics proved as revolutionary as the technology. Production costs per fuse decreased from $732 for initial hand-built prototypes in 1942 to $18 for mass-produced units in 1945. Manufacturing involved 74 different suppliers producing components. Tubes from Sylvania and Raytheon, batteries from Bulge, clockwork mechanisms from Bulova watchmakers, antenna elements from metal stamping plants. Final assembly occurred at 7 main facilities, producing 100,000 fuses monthly by 1944 and 300,000 monthly by early 1945. The industrial achievement matched the technical accomplishment. Production required creating entirely new manufacturing processes for sub-miniature vacuum tubes, precision clockwork mechanisms, and battery packs meeting unprecedented specifications.
Quality control demanded testing every fuse, a process automated using custom machines that simulated firing shock, verified electrical function, and measured radio frequency characteristics. But the most significant design choice was philosophical. The VT fuse made each artillery shell independently intelligent. Unlike conventional ammunition that relied on gunner skill and fire control calculations, VT-fused shells made optimal detonation decisions automatically. This transferred technical complexity from the weapon operator to the ammunition itself. The gunner simply aimed and fired, while the shell executed the precise timing that previously required years of training and perfect calculations. This represented a fundamental shift in weapons design philosophy. Make the ammunition smart rather than the weapon. This principle would eventually lead to laser-guided bombs, GPS-guided artillery, and modern smart munitions. But in 1943, it was revolutionary, and the Japanese forces about to face kamikaze defense were about to discover exactly how revolutionary. January 6, 1945. Off the coast of Lingayen Gulf, Philippines, the battleship USS New Mexico tracked incoming aircraft at 8,000 yards. Fire control identified the targets as kamikaze attackers, Japanese aircraft deliberately loaded with explosives for suicide attacks against American vessels. At 16:23 hours, New Mexico's 5-inch batteries opened fire using VT-fused ammunition.
The first kamikaze exploded at 3,200 yards, disintegrating in midair before the pilot could adjust course. The second exploded at 2,800 yards. The third at 3,500 yards. A fourth kamikaze veered away from the New Mexico and dove toward the nearby escort carrier USS Lunga Point. Anti-aircraft fire from Lunga Point destroyed the aircraft at 1,200 yards. Fragments of the aircraft rained into the water 400 feet from the carrier's hull. Ammunition expenditure, 47 5-inch shells. Kamikazes destroyed, 4. None reached their targets. This pattern, aircraft destroyed before pilots could execute their suicide missions, repeated across every major kamikaze offensive from October 1944 through August 1945. The Japanese had developed kamikaze tactics specifically to counter American naval defenses that conventional attacks could no longer penetrate. The logic was grimly simple. If anti-aircraft fire destroyed 80% of attacking aircraft before they could drop ordnance, then accepting 100% casualties while guaranteeing ordnance delivery, the pilot's body and aircraft became the bomb, improved mission effectiveness. That calculation collapsed against VT-fused anti-aircraft fire that destroyed aircraft beyond the range where pilots could commit to final attack runs. Kamikazes required pilots to survive long enough to aim their aircraft at targets, then maintain control through the final dive, despite anti-aircraft fire. VT fuses killed pilots at 2,000 to 4,000 yards before they could begin terminal dives. Even if the aircraft survived initial hits, killing the pilot at high altitude turned a kamikaze into an uncontrolled crash that rarely hit anything. The Battle of Okinawa, April 1 to June 22, 1945, demonstrated the complete effectiveness of VT-fused defense against massed kamikaze attacks. Japanese forces launched Operation Kikusui, 10 massive kamikaze offensives involving approximately 1,900 aircraft against American naval forces supporting the invasion. Intelligence estimates suggested the attack should achieve 15 to 20% hit rates based on previous kamikaze effectiveness. Approximately 285 to 380 ships damaged or sunk. Actual results, 34 ships sunk, 368 damaged. Many damaged ships remained operational. Total losses represented approximately 20% of predicted casualties, a reduction in effectiveness of 80%. Ammunition expenditure reports classified until 1960 revealed American ships fired approximately 1.2 million rounds of 5-inch ammunition during the Okinawa campaign, with VT-fused shells comprising approximately 65% of total expenditure, 780,000 proximity-fused rounds. The mathematics: 1,900 kamikaze, approximately 1,400 destroyed before reaching targets. 780,000 VT-fused rounds expended. Average rounds per kill, approximately 560. Against conventional anti-aircraft ammunition requiring 1,500 to 2,500 rounds per kill, the VT fuse reduced ammunition requirements by 70 to 80% while increasing effectiveness against massed attacks. Lieutenant Robert Morgenthau, commanding officer of the destroyer escort USS Lansdale, described defending against kamikazes on April 20, 1945. We detected incoming aircraft at approximately 12 miles. Fire control identified them as probable kamikazes based on approach profile. We opened fire at 8,000 yards using VT ammunition. The first aircraft exploded at approximately 7,000 yards. The aircraft disintegrated and fragments fell into the water well short of our position. The second aircraft took evasive action, but exploded at approximately 6,500 yards. A third aircraft approached from a different vector and exploded at approximately 5,000 yards. We expended 63 rounds. All 3 aircraft were destroyed before reaching attack range. The entire engagement lasted approximately 4 minutes. Morgenthau's ship survived that engagement. Lansdowne was sunk by kamikazes 4 days later on April 24th, when 4 aircraft attacked simultaneously from different directions. Even VT-fused fire couldn't cover all approach vectors simultaneously. Coordinated saturation attacks could overwhelm defenses. But the fuses forced Japanese planners to commit exponentially more aircraft to achieve the same damage. Where 10 kamikazes might have achieved 3 hits in 1944, 30 kamikazes now achieved 3 hits in 1945. The attrition mathematics became unsustainable. Japanese pilots who survived failed missions, aircraft damaged but airworthy, reported the experience in terms that revealed complete demoralization. Captured pilot interrogation reports from May 1945 include descriptions like shells that explode themselves and impossible to reach targets through explosion clouds. Several pilots reported that fellow squadron members simply disappeared in explosions at ranges where anti-aircraft fire should have been ineffective. Some kamikaze pilots attempted tactical adaptations. Low-altitude approaches, flying just above wavetops, reduced radar detection range and forced ships to engage at shorter ranges, where VT fuses had less time to achieve optimal detonation positioning. But low-altitude approaches increased vulnerability to smaller-caliber automatic weapons, 40mm and 20mm guns that didn't use proximity fuses but fired fast enough to create defensive barriers at short range. High-altitude approaches allowed earlier detection and longer engagement times, giving VT-fused guns maximum effectiveness. The Japanese Naval Command never understood the mechanism. Intelligence analysis from captured documents after the war revealed Japanese planners attributed improved American anti-aircraft effectiveness to better radar fire control, increased numbers of anti-aircraft guns per ship, and better training. Tactical recommendations focused on overwhelming defenses with larger numbers of simultaneous attacks, the only adaptation that partially worked, but only by accepting catastrophic aircraft losses. Back in Belgium, the consequences of the VT Fuze's ground deployment continued accumulating through January 1945. The 1st SS Panzer Division, tasked with capturing fuel dumps near Stavolost, documented artillery casualties exceeding 50% during a single 72-hour period, December 2022. Division after-action reports described American artillery as achieving consistently perfect airbursts and creating impassable kill zones extending 200-300 meters depth. The 12th SS Panzer Division, attacking toward the Meuse River, lost approximately 40% of its infantry strength to artillery fire by December 28th. The division was withdrawn from offensive operations on January 1, 1945, having achieved penetration of only 8 kilometers, 1/4 its operational objectives. Casualty analysis indicated approximately 70% of losses came from artillery fragmentation, compared to typical rates of 40 to 50% artillery casualties in offensive operations. By mid-January 1945, the Ardennes offensive had completely stalled. German forces were retreating to their start lines. Total German casualties exceeded 100,000, killed, wounded, and missing. American casualties exceeded 80,000. Post-war analysis by U.S. Army historians concluded that VT-fused artillery had significantly contributed to defensive success and prevented German breakthrough at critical junctures when weather conditions grounded air support and defensive lines were thinly held. General Dwight Eisenhower, Supreme Commander Allied Forces Europe, wrote in a classified assessment dated January 30, 1945, "The new artillery fuse has proven itself the most effective single ammunition innovation of the European campaign. Its deployment prevented German forces from exploiting their initial breakthrough and contributed decisively to the defensive success at Elsenborn Ridge, Stidvith, and Bastogne." German General der Panzertruppen Heinrich von Littwitz, commanding XLVT Panzer Corps during the offensive, stated in post-war interrogation, "We were told American forces were depleted and demoralized. Instead, we encountered artillery fire of a precision and effectiveness unlike anything we had experienced on the Eastern Front."
Our infantry casualties were catastrophic. Advancing through American artillery barrages became impossible. When we learned after the war that they had put radars in individual shells, it explained everything. We were fighting World War I tactics against what was essentially the beginning of guided munitions. Production statistics reveal the industrial scale of proximity fuse manufacturing. Between September 1942 and August 1945, American factories produced approximately 22 million VT fuses across multiple variants. Mark 32, the original 5-inch naval gun version. Production began September 1942. Approximately 4 million produced. Weight, 1.36 kilograms. Height, 241 millimeters. Diameter, 127 millimeters. Detection range, approximately 70 feet. Battery life, 40 seconds. Cost per unit, $18. Mark 53, modified version for Army anti-aircraft guns, including 90mm batteries. Production began March 1943. Approximately 3 million produced. Adapted for different firing accelerations and shell rotation rates. Slightly heavier battery pack for longer flight times. Mark 45, variant for 3-inch anti-aircraft guns aboard destroyers and smaller vessels. Production began July 1943. Approximately 5 million produced. Reduced size required miniaturized components but maintained equivalent detection ranges. Mark 47, modification for Army 105mm howitzers adapted for ground fire missions. Production began November 1944. The variant used at the Battle of the Bulge. Approximately 2 million produced. Reduced sensitivity to prevent ground bounce detonation. Enhanced resistance to cold temperatures. Mark 21, adaptation for Army 155mm howitzers, the heaviest artillery using proximity fuses. Production began January 1945. Approximately 1 million produced. Reinforced structure to survive higher firing accelerations. Additional variants for specialized applications, including experimental models for rockets and mortars, accounted for approximately 7 million additional units. Total production, approximately 22 million proximity fuses delivered before Japanese surrender on August 15, 1945. Loss rates, fuses that failed to function properly, decreased throughout the war as manufacturing processes improved. Initial Mark 32 models demonstrated approximately 5% failure rates. Shells that didn't detonate, detonated prematurely, or detonated at incorrect ranges. By 1945, Mark 47 and Mark 21 models achieved failure rates below 2%. Premature detonation rates, the critical safety metric, remained consistently below 0.1% across all variants throughout the war. Comparative analysis reveals the dramatic advantage proximity fuses provided. Conventional anti-aircraft ammunition achieved the following average effectiveness. Contact-fused shells, direct hit required, 2,500 rounds per kill. Time-fused shells, preset detonation timing, 1,500 rounds per kill.
VT-fused shells, automatic proximity detonation, 300 to 500 rounds per kill. This represented an improvement factor of 5 to 8 times over conventional ammunition. The cost per kill, ammunition cost only, not including gun systems, decreased from approximately $3,750 per aircraft, 1,500 rounds at $2.50 per shell, to approximately $6,000 per aircraft, 350 VT shells at $18 per shell. Despite higher unit costs, proximity fuses reduced total ammunition expenditure and achieved higher kill rates. For ground artillery, the effectiveness improvement proved harder to quantify precisely. Casualty rates depend on target density, terrain, and tactical situation. U.S. Army effectiveness studies conducted in 1945 estimated that VT-fused artillery achieved approximately 3 to 5 times the casualty rate per round compared to conventional impact-fused shells against infantry in the open. The practical effect: artillery batteries could achieve equivalent suppression with 1/4 the ammunition expenditure, or achieve 4 times the suppression with equivalent ammunition. Crew casualties, American and Allied gunners operating weapons firing VT-fused ammunition, remained essentially unchanged from conventional ammunition. The fuses posed no additional hazard to friendly forces when properly handled. Premature detonation rates, 0.1%, matched or exceeded the safety record of conventional ammunition. The most striking comparative figure: German and Japanese forces never developed equivalent proximity fuse technology during the war. German research programs explored radio proximity fuses beginning in 1942, but never achieved functioning prototypes suitable for combat deployment. Japanese programs never progressed beyond theoretical studies. Neither nation possessed the combination of miniaturized vacuum tube technology, industrial precision manufacturing capability, and resources necessary to replicate American achievements.
American philosophy prioritized ammunition effectiveness over weapon size. British forces receiving VT-fused ammunition under Lend-Lease beginning in 1944 achieved similar effectiveness improvements. Soviet forces never received proximity fuses. The technology remained too classified for sharing even with Allied nations. Soviet anti-aircraft effectiveness remained at approximately 1,500 to 2,000 rounds per kill throughout the war. Survivor testimony reveals the human dimension behind statistics. Seaman First Class James Mitchell, serving aboard the destroyer USS Laffey during the Okinawa campaign, described the experience of defending against kamikaze attacks on April 16, 1945. "We fired continuously for 80 minutes. 22 kamikazes attacked our ship specifically. The 5-inch guns were shooting those new shells. Every shot exploded near the aircraft, even when we knew the aiming wasn't perfect. We could see Japanese planes coming apart in mid-air, pieces falling into the water before they got close. We were hit by 6 kamikazes and 4 bombs, but most of the attackers never reached us. Without those proximity fuses, we would have been obliterated in the first 10 minutes. Laffey survived, though severely damaged, and became one of the most decorated ships of the Pacific campaign." Mitchell attributed his survival directly to VT-fused ammunition. Conventional shells, we would have shot down maybe 5 or 6 aircraft maximum with the amount of ammunition we had. The proximity fuses let us destroy 16 before we ran out of 5-inch ammunition. That difference is why I'm alive. The philosophical difference between American and Axis ammunition design became starkest in comparative analysis. American proximity fuses cost $18 per unit and required sophisticated manufacturing. German and Japanese conventional fuses cost approximately 50 cents per unit and required basic manufacturing. But the American approach multiplied effectiveness by a factor of 5 to 8.
meaning the $18 proximity fuse achieved equivalent results to approximately $12.50 worth of conventional ammunition, 25 rounds at 50 cents each, assuming 500 rounds per kill for VT versus 2,500 for conventional. More significantly, the American approach achieved higher effectiveness with fewer gun crews, smaller ammunition magazines, reduced logistics burden, and faster engagement times. A destroyer equipped with VT-fused ammunition could defend itself with confidence against multiple attackers. The same destroyer with conventional ammunition could hope to destroy one or two attackers before being overwhelmed. This principle, invest in ammunition intelligence rather than weapon size, would define American weapons development for the next 80 years. Every precision-guided munition, every smart bomb, every guided missile traces conceptual lineage directly to the VT proximity fuse's fundamental insight. December 19, 1944. Major Heinrich Vogel crouched in his snow-filled crater watching American artillery shells explode overhead with impossible precision. He had no explanation for what he witnessed. Neither did the Japanese kamikaze pilots disintegrating hundreds of feet from their targets. Neither would until after the war ended. The VT proximity fuse remained classified until November 1945, 3 months after Japanese surrender. When the details finally became public, military analysts worldwide recognized it as one of the most significant weapons developed during the conflict. On par with radar, the atomic bomb, and long-range strategic bombers in transforming warfare fundamentals. The Allied decision to restrict proximity fuse use over land until the Battle of the Bulge proved strategically sound. No intact German examples were recovered during the Ardennes offensive. The fuses detonated as designed, and fragments provided insufficient technical detail for reverse engineering. German intelligence never understood the mechanism. When American forces captured German weapons research facilities in April 1945, they discovered theoretical studies of radio proximity fuses dating from 1942, but no functioning prototypes. German scientists had identified the concept, but lacked the miniaturized vacuum tube technology and precision manufacturing capability to achieve practical implementation. Japanese research proved even less advanced. Post-war examination of Japanese weapons development programs revealed no serious proximity fuse research. Japanese military doctrine had never prioritized anti-aircraft effectiveness. The Kamikaze program itself represented abandonment of defensive thinking in favor of offensive sacrifice.
The irony. Proximity fuses made suicide attacks operationally ineffective, but Japanese forces never understood why their kamikaze pilots couldn't reach targets. They attributed casualties to superior American fighter protection, better radar warning, and increased numbers of anti-aircraft guns. The truth? Each shell contained a miniature radar, making pilot skill irrelevant, remained hidden until after surrender. The strategic impact extended beyond immediate battlefield effectiveness. Allied commanders gained confidence in naval operations, knowing kamikaze attacks had become manageable rather than existential threats. Ground commanders could defend positions with artillery that functioned as precision anti-personnel weapons rather than area suppression. The psychological advantage, knowing you possessed technology the enemy couldn't comprehend, provided intangible but real combat effectiveness multipliers. The Battle of the Bulge became the proximity fuse's defining moment. At Elsenborn Ridge, at Bastogne, at St. Vith, American artillery equipped with VT fuses transformed German offensive doctrine into obsolete tactics. Infantry advances that should have succeeded, based on force ratios, surprise, and favorable terrain, collapsed under artillery fire that achieved effects previously thought impossible.
When German forces finally retreated in January 1945, they carried the knowledge that American artillery had become incomprehensibly accurate. They never learned the accuracy was automatic. William Shockley, who conducted theoretical analysis of proximity fuse detection patterns, would later receive the Nobel Prize in Physics in 1956 for inventing the transistor, the technology that would eventually replace vacuum tubes and enable modern electronics. In his Nobel lecture, he briefly mentioned his wartime proximity fuse work, noting that miniaturizing complex electronics to fit within artillery shells had taught principles about solid-state devices that informed his later transistor research. The VT fuse contributed not just to winning World War II, but to launching the electronics revolution that would define the late 20th century. Production statistics reveal the scale of American industrial commitment. 22 million proximity fuses manufactured in 3 years required creating entirely new industries: sub-miniature vacuum tube production, precision battery manufacturing, miniaturized clockwork mechanisms. The industrial knowledge gained manufacturing millions of tiny, shock-resistant electronics packages would directly enable post-war consumer electronics industries, hearing aids, portable radios, and eventually integrated circuits. The lesson of the VT proximity fuse resonates beyond its immediate tactical impact. While Germany invested in larger guns, heavier tanks, and jet aircraft, America invested in making existing weapons more effective. While Japan trained pilots for suicide missions accepting 100% casualties, America developed technology that killed those pilots before they reached targets. The philosophical choice, enhance what you have rather than build something bigger, proved strategically decisive. Major Heinrich Vogel survived the war. In a 1967 interview with American military historians researching the Battle of the Bulge, he described his December 1944 experience witnessing impossible airbursts. "We thought perhaps your gunners were the best trained in the world. We thought your fire control computers were far superior to ours. We thought maybe you had developed some acoustic ranging system we couldn't detect. When I learned in 1946 that every shell had a tiny radar, my first reaction was disbelief. My second reaction was understanding. Of course we couldn't advance through your artillery. Your shells were smarter than our tactics. That's why Germany lost." The VT proximity fuse was not a miracle weapon that won the war alone. It was a technological revolution that multiplied the effectiveness of weapons America already possessed, provided decisive advantage at critical moments, created psychological dominance that undermined enemy tactics, and demonstrated principles that remain fundamental to modern warfare. Precision matters more than size. Intelligence multiplies effectiveness. Technological advantage, properly exploited, provides strategic impact far exceeding its tactical specifications. The shells that exploded perfectly above German infantry in the Ardennes, that destroyed Japanese kamikazes before they reached their targets, that turned anti-aircraft guns into 5 times more effective weapons, those shells contained the future of warfare.
Every guided missile, every smart bomb, every precision munition deployed in the 80 years since traces its conceptual heritage to a simple insight: make ammunition intelligent, and you transform everything. And in that single fact lies the entire story of why technological innovation, combined with industrial capacity and strategic patience, defeats larger guns, heavier armor, and greater willingness to accept casualties. The VT proximity fuse proved that wars are won not by building bigger weapons, but by making every weapon you fire dramatically more effective than anything the enemy can deploy against you.